we have this tricky word, significant, which means, like many words in math, means something in real life and means something different in statistics. They're kind of related, but are they the same? So the three options were there is low uncertainty in the effect is unlikely to be due to chance, or the effect is large. And people said, 13 people said the effect is unlikely to be due to chance, 3 people in each of the effect is large, and 3 people in there is low uncertainty in the effect. So pretty big majority on the effect is unlikely to be due to chance. Unfortunately, the correct answer is, you guys got it right. The effect is unlikely to be due to chance. So most people got it right. A lot of people mix up these two things because if the effect is large, or if there is low uncertainty in the effect, that often implies that the effect is unlikely to be due to chance. So this is like the real thing, and these two things together will sort of imply the first one. But the first one is the right one, so it looks like you guys have a good understanding of this. Let me draw a quick picture to sort of recap what is going on and remind you of this stuff. So here is how I kind of visualize this stuff. You have your data over here, which is some x's and some y's. Maybe let's put them together in pairs. X's and y's. And then you kind of do something to it. This is like your model. So for example, one thing you might do is compute these coefficients, beta hat 0, beta hat 1, etc. And I think this is the thing that people forget, is that when you go from data to the model, the stuff you get is going to be random, right? The data is always random, always has randomness baked into it, so the answer you get is also going to be random. So something like beta hat 0, which is very often it's like the average of the y values, 1 over n data times the sum from I equals 1 to n data of the y values, that will be a random number. And the nice thing about this random number is even though all the individual data points are random, some of the randomness gets washed away by doing an average. So if you have more data points, you get less randomness. So by having a bigger data size, you are shrinking the amount of randomness. And I think this was one of the things we finished off with last week, was we showed that the variance is 1 over n data times the variance of y. So the variance shrinks like 1 over the number of data points. If you had sort of an infinite data set, then you would have no randomness. But for 100 data points, you have shrunk it by a factor of 100. It shrinks like this. And so even though beta hat 0 is random, you hope that the amount of randomness is small. And you can kind of draw this as a little diagram. You can say, like, here is beta hat 0. Here is what I measured, beta hat 0. And then you can sort of imagine this imaginary like peak where you're thinking of like, okay, but it's random, so it could be sort of anywhere in here. This is like you imagining. How do I draw a picture of somebody imagining? I draw a little person. And I think this is like, could be here. So if you're a good data scientist, even though your model says beta hat 0 is 3, you should think, okay, but it actually could be anything between like 3-point blank and 2-point blank, where the blank depends on how big is the typical size here. And this is the variance. The typical size is the square root of the variance. So this is the standard deviation, beta hat 0 plus sigma, where sigma is the square root of the variance, the standard deviation, beta hat 0. And here is beta hat 0 minus sigma. So that's like a little bit to the left and a little bit to the right. That's what we call a confidence interval. And if you make it bigger or smaller, you can be more or less confident what it is. So a very common thing people do is do 2 standard deviations, and then they say this should be hopefully a 95% confidence interval. So if you know your estimate for beta hat 0, and you can estimate what sigma is, you can be like 95% sure that the true answer is somewhere between beta hat 0 minus 2 sigma to beta hat 0 plus 2 sigma. That's this idea of confidence intervals. That is what we finished off with on the last class.
Sir?
Yeah.
So the beta hat 0 is something we predict or something else?
Oh, beta hat 0 is this formula, right?
Okay.
The average of the y value.
Average of the number. So
Yeah, that's what we ended up with
Yeah.
last time. So is it something you predict? I mean, yes, you started with the data and then you estimated this. There's sort of some true value out there, which is that, remember, the true thing that we actually would like to have is maybe what is the true value of the expected value of y. And we will never know the true value of the expected value of y. Y is some real life process. There's some unknown real life thing, but this is our best guess with the data we have. This is the true versus measured situation. And that's why we have a hat. This is our predicted. Okay, hopefully that answers the question. Any other questions? Yeah.
So there was like concept about t statistic.
What is the t statistic? Okay. The t statistic is telling you, I drew this picture, and last class I made sure that they were exactly Gaussian, right?
Yeah.
When they're exactly Gaussian, you can look up on a table of Gaussians, and this 2 is actually like 1.96. And that's the translation from the 95% confidence interval to the number 2, is you look up this standard thing. There's a very nice function called the Gaussian random variable, or Gaussian, if depending on how you pronounce it. It's the same as Parisian versus Parisian, but it has this formula. This is the Gaussian random variable, and I've done everything with this. That's where I got the 2 from the 95%. There is something called a t statistic, which is saying in certain situations, you know it's not quite Gaussian. There's another formula called the t distribution, and it looks very slightly different. And it looks like this. I don't know. It looks slightly different. So it's like, this is like a t distribution. So it's very slightly different than the Gaussian. And then you have to look up a different table, and it depends on some parameter t. But the idea is the same. There is some amount of randomness, and you use what you think you know about the randomness to try to get this confidence interval. It's just a more detailed way of doing it. If you take a stats class, they'll go into a lot of detail about this t distribution and so on. In this course, we're not going to make a big deal out of it because we're going to show you something called the bootstrap, which is like, how do you measure it with data? So don't do a bunch of fancy math. Just like take your data set and like use that. So it's the same way we said we're going to use cross-validation to measure errors. We're not going to try to measure the error some other way. So I won't say anything about t distributions other than what I just said. You should just think of them. They're like the Gaussian, but not. That's what it is. Great question. Anyone else? Okay, so how does this relate? You guys all knew what this idea of significant means. I'll write it down just to be sure. So significant, strictly speaking, means the confidence interval. I say like contains a non-zero effect. Contains a non-zero effect. And so for the very simple thing of is the mean something other than 0, it's just looking at this interval and does this interval contain 0 or not? Is on the x-axis. Is 0 somewhere in here or is it not in here? And that's what significant means. And that means it's unlikely to be due to chance because if the true answer was 0, then it could be sort of, if 0 is in this interval, then there could be no effect and you would still see what you're seeing. So basically, you shouldn't think of any of the numbers you get as being actual numbers. You should think of them as like fuzzy numbers that could be a little bit smaller or a little bit bigger. And if you're trying to say, my number is definitely not 0, then the little fuzzy interval you draw around your number should not include 0. That would mean your fuzzy number, even though you don't know what it is definitely not 0. You can sort of rule out it being 0 with high confidence. If you can't rule out 0 being there, then it's not significant. So maybe another way to say it is the opposite. Not significant. Significant. Maybe it's easier to think of this. The effect could be 0. Could be 0. And if the effect could be 0, then 0 is in our confidence interval. CI includes the zero effect. So that's something to get right. The zero effect, sometimes people call that the null hypothesis. Null and zero are kind of synonymous. So they're saying, if there was no pattern here, that's the null hypothesis. Could we see what we're seeing, right? If there's no pattern at all, if these numbers are just random and are not, in the example I gave, I'm just looking at the mean. If the null hypothesis is that the mean is zero, then you just want to rule out the fact that your little fuzzy interval, your confidence interval, if that contains zero, then it could just all be due to chance. There could be no effect here, and you would still see what you're seeing. On the other hand, if it's far away from zero and it doesn't include zero, then you would say it's significant. Okay, but you guys all got the question right, so maybe you all already know this stuff. Any questions or comments about this? All right, very good. So I have a little notebook that I made that you can check out in your own time. It's on the course GitHub, and it kind of does this picture, not this one, this one. So we looked at the first one last time. Let me sort of advertise it a bit. We did the one-dimensional one, which is the zero-dimensional one, which was exactly this thing where the confidence interval for purely random noise with zero mean, the confidence interval was between negative 0.2 and 0.2. So if you get a measurement and it's like 0.1, and you know that the error size is like 0.2, that's could very easily happen even if there's nothing to see here, right? If it's just pure randomness, the size of the interval is telling you sort of how big it's going to be. So you shouldn't get excited when you see something like 0.15. That could be just due to pure chance in this particular problem. So we did that last time. The other thing in this notebook you can check out if you want is I did it with linear regression. So I had some data points. The data points are random. They have a secret blue line that they're following. So just like in the cannonball problem, there was a secret function we were trying to find, and cannonballs around the true value. Here, it's some straight line, so there's a secret slope and a secret offset that you have to try to guess. And then I ran the regression on this. I generated the data over and over again, and I got a bunch of betas. So here's one example, right? The true thing is the blue. Here's the one I estimated with those data points is the red. But you can run it over and over and over again and do this kind of thing. So here I did it over and over and over again. I think I did it 20 times. Yeah, trial 0 to 20. So I did it 20 times. Here are the values I got for beta 0 and beta 1 with a new data set every time. And you can see that you never get the perfect dark blue line. You get something that wiggles a little bit around it. And the standard error is the confidence intervals tell you how close you should expect the measurement you get, how close should it be to the secret mean. And you can draw them, so you can draw it like this, where you draw x versus y, but you can also draw them in sort of parameter space. In parameter space, you have beta hat 0 and beta hat 1, which I left off the hat here because the hat is annoying to draw in this programming language. So there's beta 0 and beta 1, and you can see they're sort of typically around 2 and around 3, but they jiggle around a bit. So this is a very important thing that you must not ever forget. Every time you get numbers from data, they are not real numbers. They are random numbers that can jiggle a bit. And this is like understanding how much they jiggle. The green square I drew there is what you get by theoretically calculating the standard errors. And that's a 95% confidence interval. So I repeated this experiment 20 times. It should be inside the square 19 times out of 20. And actually, more accurately, each dimension should be in there 19 times out of 20. So we should have one case where it leaves on the x-axis and one case where it leaves on the y-axis, which is like 2 mistakes, sort of, right? And you can see, actually, there were 3 mistakes. So these 3 points, they left on the x-axis, but they are all within on the y-axis. So we were expecting 2 mistakes out of 40, and we got 3 mistakes out of 40. So the theory is pretty good. That's how you do stuff in stats class. You figure out these errors, you do a lot of math, you figure out how big is the error, and then you run your model, and you're like, I'm pretty sure the error is this much. Okay, I won't say too much more about that, because like I said, we're going to do a data version of this, but I think the philosophy is could not be more important. When you do stuff with data, you get random answers. You need to know about the random answers and know that they're not real numbers, right? They can change a little bit. Even if you have the exact same distribution, you're going to get a different answer depending on how many data points you have and things like that. Questions or comments? I sometimes boil this down. Basically, every time I read a newspaper article or something, and they're like, we measured this, and the number we got was 7. I scream a little bit. It should be 7 plus minus 2. You should never report a number as that thing you got from a data set. You should always report a number and also how sure you are about where the number is. One way is an upper bound and a lower bound, so 7 plus minus 2 is saying it could be between 5 and 9, and that would be fine. Another way, you could report the error separately or something, but it's misleading to say, I got the number 7 for something you get from a data set. Okay. Questions or comments? So now we're specifically going to look at this stuff. This was all 0-dimensional. The first thing we did was 0-dimensional. It was just the y values on their own with no x's. Then we did 1-dimensional, which was we had x values and y values. But a lot of weird, tricky stuff happens when you start going into higher dimensional things, and things get very confusing. So basically, the rest of this lecture is going to be on confusing stuff that happens when you have multiple input dimensions. And in real life, you will often have hundreds and hundreds of different dimensions. That's why linear regression is good, is it does well sort of with these multiple different things. So you must understand the confusing stuff that happens in high dimensions. So the first question for you is something about these multiple dimensions. And I have a little picture. So here is one with an x1 and an x2. So suppose we have a system of 3 related variables, x1, x2, and y. So you can imagine something like x1 is how many hours somebody studies in a week. x2 is the grade they got in their high school linear algebra class. And y is the grade they get on the final exam on some course later in the future. And you have these 3 variables. You can plot them like this. So the y value is a color bar now, right? And I have x1 and x2 plotted. So don't mix this up with what I was doing before. Now the y value is the color, right? Here's the y value on the color bar. x1 is on this axis, and x2 is on this axis. And every point is one of my data points, all right? And the question we want to do is we want to predict how y depends on x1 and x2. Specifically, we want to know how does x1 affect y? That's what we want to know. So it's how many hours a week should I study? How does that affect my final grade? Or something like that. So here's what it says in the question. We want to understand how x1 affects y, so we run a single variable regression on only one variable. So y equals beta hat 1x, and we use linear regression to estimate the value of beta hat 1. So we put it into our linear regression formula, we get the value of beta hat 1. Which of these describes the interpretation of beta hat 1 the best? So beta hat 1 is something that came out of the computer, but now I'm asking you to use your skills of thinking and interpret beta hat 1 in English words, okay? And the 2 options are basically this blue arrow and the red arrow. So the red arrow says increase x1 with x2 fixed, so you're only increasing in the x1 direction. And the blue arrow says increase x1 and x2 at the same time. So x1 and x2 both increase. And I think the way I wrote out these 2 options are like this. When x1 increases by 1 unit, allow the other variables to change accordingly. That's the blue arrow. The value of y increases by beta hat 1 units on average. So when you increase x1 and x2 along that blue arrow, then y increases by beta hat 1 units. Or the other option is x1 increases by 1 and x2 is fixed. That's the red arrow. Then y increases by beta hat 1 units on average. So those are the 2 choices. I personally find this really subtle, and people mess it up all the time. It's really good to have a solid understanding of what's going on here. Any questions or comments about the question? Okay, let me set you loose on the question. Have a couple minutes. Think about what it is and how confident you are on your answer, and then we'll take it up in 2 minutes. But feel free to chat with people. Maybe you have some notes on linear regression you want to consult.
input, which is also an example of multiple regression. Multiple variable. टू फिक्स कैसे हो सकता है भाई?
Okay, put in your guesses of what you think. I only have 3 answers so far, but put in what you think it is. And let's take a look at what people said. Okay, I'm going to reveal the answers in a second. I would like us to have a consensus on this. So here's what I'll do. If it's more than 2/3 of people in one answer, then I'll reveal the right answer. But if it's between 1/3, 2/3, like if it's close to 50-50, where the most popular answer is not double the second most popular answer, then I'll revote it. Okay, so we're gonna have a discussion and try to see, maybe we'll get some arguments. But that's the plan. Okay, let's. What did people say? So 13-7, I said has to be double. All right, double 7 is 14. So you guys are close to a consensus, but according to what I said, you are not. And I guess blue has a pretty big majority, but not quite a 2/3 majority. So, like I said, I'm gonna open it up again. We're gonna do a revote, and what I would like for you to do, if you think it's blue, come up with like a really solid, here is the reason why it must be this one, that you could explain to somebody. Okay, so let me revote it, and we'll see if we can get to a majority, or a consensus rather. All right. So, okay, I'm gonna open it up again. Feel free to chat and see if you can come up with a nice explanation of why. Okay. Okay. And okay, it's open again. Take another. All right, there's like 10 seconds left. Put in your updated guesses. Even if you don't want to change your mind, you must revote. Okay. Let's see what people said. Okay, I guess I had 20 people before. Now I only have 19. Okay, maybe Somebody's about to press a button. This time we are on 15 to 4. Okay, so people have switched to the blue arrow. Here is my thinking. Here's my thinking. So we have the equation y equals beta hat 1 x 1. Okay. But now increase x1 by 1 unit. So y equals beta hat 1 times x1 plus 1, which is beta hat 1 x1 plus beta hat 1. So it went up by plus beta hat 1. So y went up by beta hat 1 when x1 increased by 1. And to me, this looks like the red arrow, right? I increased x1 by 1. Y went up by beta hat 1. That's the red arrow. But everybody voted for the blue arrow. The blue arrow. So the blue arrow says, like, you vary x2 or something. What's wrong with what I said over here? What is missing? Yeah.
You assume that it's also the y equals beta y hat times x1 plus 0 times x2?
Okay. Okay, plus 0 times x2. Sure, I can put that on. Plus 0 times x2. And then look, if x2 changes by some amount, x2 plus some change in x2, you multiply it by 0, that's still 0. So I'm still happy. Yeah. X1 increased by 1. Yeah, I haven't thought about this idea of adding 0 times x2. That's a nice way to think about it. So I added 0 times x2. I guess the problem is because it's a 0 times, it doesn't matter if this changes or not. So if it's some change, you multiply it by 0. If the amount of change is 0, then you multiply it by 0, and it's still there. So whether or not, so I guess there's two options here, right? There's option, the blue arrow option says change by some amount. That's the blue arrow option that you guys all picked, like delta x2. And the red arrow says change by 0. Change by 0. Right? Those are the choices. You can either change by some amount in x2 or you can change by 0. But either way, you multiply it by 0, and so you get the same answer. So I think this thinking of 0 times x2, I don't think tells you which one is right between the red arrow and the blue arrow, because it could sort of come out both ways. So that's, I wouldn't add on as 0 times x2. I think it's actually an interesting way to do it. It's a nice, so it's like, let's think of the model where beta hat 1 plus something times x2, but the something has to be 0. That's a nice way to include x2 sort of implicitly in your model. Yeah, I don't see how it answers the question. It's a nice thought. Maybe somebody else sees how it should answer the question. Yeah?
Since we're assuming that the variables are correlated, that means they must move together in some sense.
Right.
So we include like an interaction term that might help us capture.
Okay. So what do you want to include in? You want me to write down something like something times x1, x2, or something like that, or? Yeah. So I think you're saying if you include an interaction term, that interaction term will tell you something about how x1 and x2 are related. On the other hand, the question I'm asking is, if you run the model with only the x1, what is the interpretation of the beta hat 1? So I think you're answering it, you have the correct answer to a different question, which is, if you wanted to understand how x1 and x2 are related, you would run something like this, and that would help you figure it out. But I want to answer the question, what does this mean when you run it with nothing else? Yeah?
Yeah, like triple picture results.
Yes. I can go back to the plot.
Yeah, so when we only include the variable x1,
Yeah.
we're going to like project all the point onto x-axis.
Uh-huh.
We don't care about the variation of the y x2 amount of x2.
Okay.
So, of course, when the x1 increased by beta y had a unit. And,
Yeah.
there are some variance in x2, but we don't care about that at all.
Okay, so is this an argument for the red one? This almost sounds like an argument for the red arrow. Is it you're arguing for the red arrow? I think you're saying this is another way to think about it. Take this whole data set. We have x1 and x2. And imagine taking the data set and smooshing it onto the x2 axis, right?
Yeah.
Whatever the value of x2 is, we don't care. We smoosh onto the x2 axis. We smoosh down. Now we have some dark colored points over here for negative values of x1. We have some light colored yellow points over here for positive values of x1. But the information on what x2 value it was lost. When you smoosh it down, it's just some one axis thing. Okay, and then we run the regression only on those values, right? So does this tell me, is it the red arrow or the blue arrow? Because the arrows got smooshed together when we did this, right? The blue arrow and the red arrow are now identical.
Yeah, but I'm choosing the blue arrow.
So you're choosing this, so why is this an argument for the blue arrow?
Since there are some changes in x2 variable, but we
Uh-huh.
just ignore them.
I see, so you can't see them.
Yeah.
Okay. So you're saying there's a secret thing that involves the x2 variable that we can't see. And therefore, I don't understand that. Everything you're saying is good. I like that way you're thinking in the picture. I just don't understand the conclusion that it means it's the blue arrow. To me, everything you've said is like an argument for the red arrow. It's like, look, we're smooshing it down. The blue arrow doesn't exist. Like this is like the kind of thing I'm getting, the vibe I'm getting from what you're saying. Maybe there's like a way to think about it where you're like the conclusion is the blue arrow is correct, but I'm not seeing it. Okay. I think you don't like you're on the right track. It's just I think there's like a logical step missing. Yeah.
I would like to ask a question.
Yes.
So my question is, if y, x1 and x2 are varying,
Yeah.
x1 is increasing and x2 is also increasing,
Right.
and you definitely have beta 1, x1 and beta 2, x2.
This is a great. Okay, let me write. I'm gonna write down part of what you said, just because I think this is the crux of what you said. You said, "Do we definitely have? Do we definitely have beta hat 1 and beta hat 2?" I think this is the most important part of what you just said. What do you mean by this?
Because if x2 is also increasing,
Right.
then x2 also have an estimate, a beta estimate.
Okay.
So my question is, if both x1 and x2 are increasing, because for the question you asked, if x1 is increasing and x2 is varying, or maybe probably the
Right.
other variables are also varying, it means
Right.
they are changing in some way, they are either increasing or decreasing, so they will also have an estimate.
Yeah, so this is a great question. In my problem, I only have, as stated in the problem, I said I ran a regression with y equals beta hat x1, and beta hat 1 is what came out of my computer, right? So I took my data set, which was x1, x2, and y, and I ran a regression only with x1 and y, and the computer spit out this beta hat 1. That's what I mean by beta hat 1.
I'm actually asking my question to answer the first.
Okay, great. Yeah.
I mean, like the backward kind of
Yeah.
thing. So if here you go only with beta 1,
Uh-huh.
but then in the situation where x1 and x2 are varying, or x1 and x2 are increasing, or all the variables are varying,
Right.
you also have like different estimates. So if you just have beta 1, then it means it's only x1 that's increasing, all others are fixed.
Okay, so this is an argument for the red arrow.
Yeah.
Okay, so I like that. So you're thinking that in a different world, we might have both a beta hat 1 and a beta hat 2. And so you could like sort of like, again, this is a person thinking, you're like, what if I ran it, right? In the original question, there was only a beta hat 1, but you could imagine a universe where you did a y equals beta hat 1 x1 plus beta hat 2 x2, right? Y equals beta hat 1 x1 plus beta hat 1 x2. So imagine this. And then I think you were reasoning about this thing. You were saying, in this one, right? In this one, for sure, if you increase x1 by 1 and you fix x2, then you increase by beta hat 1, right? Because then this is the thing that was ambiguous before because we were multiplying by 0. Now we're multiplying it by beta hat 2, so it's not increasing by 0. We can tell the difference, and for sure in this one, beta hat 1 represents increasing x1 by 1 and leaving x2 alone. So for sure, this one is the red arrow. So beta hat 1 means x1 goes up by 1, and x2 stays the same. And we can tell the difference by adding 1 to x1 and leaving x2 as x2. Then y goes up by beta hat 1. So very good. So in this one, beta hat 1 is the red arrow. And then the last thing you said is, that means beta hat 1 is the red arrow, right? Okay, very good. Who is convinced by this argument? Yeah.
I just want to add something. I feel like something is missing in the picture. I feel
Okay.
like there should be another arrow that is perpendicular to the red one, and when you add those two, you get the blue one. And the missing one should be the one that
this one.
representing the beta 2.
Ah, there's an arrow that goes this way,
Yeah.
which is actually just the y-axis.
Yeah.
That is increasing x2 and leaving x1 alone, right?
That should be the beta 2 we're talking about.
That's the beta 2. Yeah, I agree. So in the little thought experiment, we can also say, here we can also say beta hat. We can also say what beta hat 2 means. So let's increase our thought. Beta hat 2 means x2 goes to x2 plus 1. x1 goes to x1 fixed. So okay. So what have we? I love this idea. I think this one there is like very little ambiguity about what it means. This one makes sense. When you only have x1 and x2, and you run a regression with x1 and x2, it makes perfect sense what it is. And you guys are exactly right that in this little thought arrow, beta hat 1 means the red arrow. Where's my picture? Yeah, so in this one, for sure beta hat 1 means the red arrow. And beta hat 2 means the green arrow, whatever, going vertically upwards. Okay? But now the question is, if you run a regression with only one variable, right? With y equals beta hat 1, and you just you don't put it in the computer, right? You just delete it from, you temporarily delete it. You save a copy of it in case you want it later. But you delete x2 and you just run with x1, then what are we doing? Is it this red arrow again? Because we said it's the red arrow. And then now I'm saying okay, we're doing this funny thing of deleting it. You might say, why would anybody do such a thing? On Wednesday's class, we're going to spend a whole class talking about deleting variables and why it's good. And it's going to seem, it's counterintuitive, but it's true. So it's very important you understand what these things mean and what they don't mean. That's why I wanted to get into this. Okay, let's take a little straw poll. Who's not confident on which arrow is the correct arrow? Who still thinks it's the blue arrow? Who now thinks it's the red arrow? Who didn't put up their hand for any of the options? Okay, let me let you guys vote again. I'm very excited. This is fun. I'm gonna have you vote one more time. Have a chat. I promise I'll reveal the answer this time. Okay? I tried to make it interesting, and hopefully it's worthy of your thinking. Okay, take 2 more minutes. Okay, there's like 10 seconds left. Put in your final guess, and I promise I'll reveal the correct arrow this time, regardless of the outcome. Okay. All right, now we're back to 10 to 9. This is great. I think the point of this is it's very easy to kind of mix these things up, and it's actually like a difficult philosophical thought to figure out what the hell is actually going on. This is the reason I ultimately decided not to just record a video about this, because it's really easy to just watch a video and like nod your head and be like, I understand everything, that's fine. But if you think about it, it's actually hard. So now we're at 10 to 9 for the blue arrow, and the correct answer is the blue arrow. So you guys actually got it right. Let me tell you two different ways of thinking about it. One is to realize that there is something always missing. When someone says y equals beta hat x1, even without all this other stuff, when somebody writes down y equals beta hat x1, and that is their model, there is something missing that people don't write down that should absolutely, like, sort of, if you want to understand these questions, you need to put it there. Does anyone know what is missing? There's something that should be there in the equation. The irreducible error, right? It should say plus epsilon. It should say plus epsilon. If you want this to be an equal sign, you better put an epsilon there. And epsilon, the irreducible error, represents everything else, right? Epsilon is a function of everything else. In real life, you think of epsilon as like stuff you didn't measure, right? It's like I measured how many hours you spent, but I didn't measure like your IQ or something, right? So it's really a function of everything else. So epsilon represents everything else. And in this particular case, everything else includes x2, right? This is the thing that I think it tricks you, is that everything else in this case includes x2. So the irreducible error in this case, because I just decided to ignore the variable x2, the irreducible error is going to absorb that x2. That's what's going on, and that's why like you can write these tricky arguments down. If you don't write the epsilon and keep track of what happens, then you're going to get mixed up. Here is the other way I can think about it, which I think is actually even better if we have this on the board. If you imagine this universe of beta hat 1 x1 plus beta hat x2, and you compare it to this universe, where y equals beta hat 1 x1. Let me write the epsilons kind of explicitly. This epsilon depends on other stuff and x2. This epsilon depends only on the other stuff. So the difference between these two models is the irreducible error here is like depends on x2, and the irreducible error over here is all the stuff other than x1 and x2. Okay? And I think the very confusing thing about writing these both on the board that you must be super careful of, these things are both called beta hat 1, but they represent totally different things. Like you should not think that these are the same value. They are absolutely not the same value. And in fact, like beta hat 1 in this one and beta hat 1 in this one, you should just think of them as totally different things. Like if you have a different model, the coefficients mean different things. Here is an easy way to find the relationship between these two things. So let's calculate the blue arrow in this model, in this one. So the blue arrow says, let x1 change by 1, and let x2 change by, I guess it's, okay, I can write out a formula for it, by the right amount. I'll just say the right amount to not put fancy formulas on there. It's the amount so that if you were predicting x2 based on upping x1 by 1, you would get the best possible prediction. And then you see that y changes. Where'd my mouse go? Okay. So y equals beta hat 1 times x1 plus 1 plus beta hat 2 times x2. I'm going to call it delta x2 plus epsilon of the other. The other stuff doesn't change. So in this case, you get beta hat 1 plus beta hat 2 times delta x2 plus beta hat 1 x1 plus beta hat 2 x2 plus epsilon of the other. So the amount of change here is beta hat 1 plus beta hat 2 delta x2. I want to emphasize this is the double regression. Let me put a little like 2 everywhere. This is when you do a regression with 2 variables. These are the things. 2, 2, 2, 2. Let's put them everywhere. So when you do a regression with 2 variables and you change x1 by 1 and you change x2 by the right amount in that blue arrow direction, then y changes by the sum of these things. On the other hand, over here, here you change beta hat 1. This is the 1 variable regression. Let's add a little 1 everywhere. So x1 goes up by 1. Other comma x2. Here's the point: is that this error will be different. This is x2 plus delta x2, but you're going to get beta hat 1 1 times x1. Let me write it the other way. So okay, that's actually fine. Beta hat 1 times x1 plus epsilon of the other stuff. Okay, so let me highlight these things so we can compare them. So in the 2 variable regression, you get a combination of the 2 coefficients. That's how much is changing along the blue arrow. And in the 1 variable regression, you only have 1 change. But actually, these 2 things are going to be the same. So the thing that is like confusing is that they're both called beta hat 1, but you got to remember this is the beta hat 1 with the 2 variable situation. That's beta hat 1 in the 1 variable situation. And actually, that's what these things will be. So when you do a regression with just 1, because of the way these irreducible errors work out, the amount you get is some combination of the 2 variable coefficients, and you're basically taking all of the x2 dependence from the irreducible error and you're baking it into the coefficient here. So it really is the blue arrow. And to kind of convince you, like for sure to convince you of this, I wrote a little package here where we do this. Not this one, but this one. Okay, so here's the picture that the question came from. Let me zoom in and show you what happens here. So I made some data. The data is jointly Gaussian. So there's x is Gaussian, and they have a correlation. There should be a little correlation here. Where's the correlation? Okay. Here we go, 0.75. So x1 and x2 have a correlation of 0.75. So if you increase x1 by 1, x2 increases by 0.75. So the little value I said over here, the right amount, in my example is 0.75. In my example. So when x1 increases by 1, x2 on average increases by 0.75. You can write that down in a more mathematical way, but that's what's going on here, and that's what the picture is. Okay, so then I generate some data. The secret is that y really is linear. So it's beta 1 x1 plus beta 2 x2 plus noise. The noise is itself random. And this beta 1, there's no hack. It's like the real truth. In real life, it won't be this simple, but this is a nice simple example for you to understand. So that's where the picture came from. And the real values of beta 1 and beta 2, what are they? They're 3 and 4. So those are like the true values. Here is the linear regression with only x1, right? And so I ran it. This is the true thing. This is the estimated thing with beta hat. And here's what you get. So the true thing is that beta 1 is 3 and beta 2 is 4. The correlation is 0.75. In the model, beta hat 1 with only one thing came out to 6. Why did it come out to 6? It's because it's 3 plus 4 times 0.75. So when you change x1 by 1, you kind of think of moving x2 up by 0.75, and the true amount of change in y will be 3 plus 4 times 0.75, and that corresponds to what we measure, which is 6. On the other hand, if you really measure it the right way with x1 and x2, then you really get 3 and 4. So this really for sure shows you that it is really the blue arrow, and like thinking about these two things and thinking about the noise, which I left off here because everyone always leaves it off, is how you sort of reconcile these things in your brain. So I think this is the best way, to me, this is the best way to think about it, is to think of this universe and compare it to this universe. The moral of the story that people often write down is when you change a variable, or so maybe a better way to say it is like this. Beta hat I means three things. You change xi by 1, right? So you increase xi by 1. You leave everything else in the model fixed. Everything else in model fixed. And you change everything that's not in the model. So everything not in the model gets changed. Everything not in the model changes with xi. So in our example, we said we have x1 and x2. If you do a model that leaves x2 out, then the interpretation of the coefficient beta hat 1 means you change x1 by 1, and you will change x2 with it because it wasn't in the model. If x2 is in the model, that means you are leaving it fixed when you do it. And I guess the other corollary of this thing is warning. The coefficients are very model dependent. So if it doesn't really make sense to say the beta hat value is 7 without also saying beta hat value in this particular model with these particular things. This is exactly my model. If you just tell somebody the value, you say that the coefficient in front of x1 has no meaning on its own without specifying which things are fixed and which things are not fixed. So the coefficient in front of xi changes depending on who is included, excluded. That's another way to say this warning. So you should be very careful with these kinds of things. I think a lot of people think there is some actual coefficient out there that we're trying to estimate. And that's only true once you've specified exactly the model, right? Exactly which model you're trying to do. And it's equivalent to saying who is in the error and who's not in the error. But this is the important misconception that you should not miss. Okay, it's sort of confusing because it's confusing in real life, but hopefully it's minimally confusing now. Any questions or comments about this? So I like that we spent some time on it and made sure to get it right. Here is a follow-up question. If you've absorbed this kind of stuff, here is the follow-up question, which I want to do positive, this one. Okay. True or false? If the coefficient beta hat 1 in the regression y equals beta hat 1x is positive, then the coefficient of beta hat 1 in the regression y equals beta hat 1 x1 plus beta hat 2 x2 must also be positive. So we saw before it can sort of change. Can it change from being positive to negative, or is that off? I'll let you think for a minute.
अगर smaller है तो beta का next one बड़ा होगा तो beta 1 की बात होगी
Okay, there's like 15 seconds left. Put in your guesses on the true false question. Okay, let's take it up and see what you said. Once again, whether or not something is positive in this model, like a lot of times you don't actually care about the value, you just want to know if it's positive or negative. It's like if x1 represents how many hours I study and y is my grade, I want to know, does studying more help me get a better grade or not? Like, should I study more or should I study less, right? Do we want to increase the x1 or decrease the x1? That's the question for positive or negative. Like, that's why positive or negative is so important. What did you guys say? 17 people said false. The correct answer is false. So very good. If you have kind of like a pedestrian understanding of this stuff, this is so counterintuitive, right? It's like whether or not studying more hours helps your grade depends on what else is in the model, right? So for example, there could be that it's just like there's some other external thing, like how many carrots you eat. That's the only thing that matters, right? And then the thing is, like, people who study a lot tend to eat a lot of carrots or something, right? And these kinds of things can confuse you. You gotta be really careful with when you interpret the coefficients, whether they're positive or negative. It really, you have to kind of think of keeping everything else fixed, right? So this is the real thing, right? If it's positive, that means everything else that is in the model is fixed, right? So maybe for somebody who eats 1 kilogram of carrots every week, for them, studying more is actually bad, right? Let me show you an example that I think is quite kind of illustrative of this. Here is some data. Here's an x1 and a y, and there's 2 data. So let's imagine that y is people's grades or something, like how good they do, and x1 is how many hours a week they study, right? So based on this graph, does studying more help you or not? And I phrase this question like this. Increasing x1 is associated with a positive change in y, or is increasing x1 associated with a negative change in y? And I want you to look at this graph and like, you know, if you're a data scientist and someone gives you this graph, what would you say to them? Is increasing x1 associated with a positive change in y or a negative change in y? Okay, you tell me. There's 2 options, so it's kind of like a true or false. Oh, I guess I left all that apply on. Don't choose both. If there's one, choose one or the other. That's a mistake. Okay, let me give you, again, another minute and a half to see this one. Okay, there's only a couple of seconds left. Put in your guesses. And again, this is a weird one, a tricky one, so it's good for discussion. There's no like, this is obviously the answer. Okay, what did people say? Let's see. Okay, 16 out of 20 people big majority said increasing x1 is associated with a negative change in y. I would kind of agree with this. This is like, if you intuitively look at this, you're like, there's a group of people over here, and if you're in the, like you increase x1, it's going down, and this is also going down. But the confusing thing is if you just run, right? If you just run the regression, so if my data set looks like this, if you run a regression, y equals beta hat 1 x1, which is what some people would do to determine the answer to this question, is increasing x1 associated with increasing y or not, they would say, run the regression, is it positive or negative? What will happen if you run the regression? Does anyone want to tell me how to draw the line if you run this thing? You're doing it in the air. Is it positive or negative? It's positive. It's positive. So remember, it's finding the line that minimizes the square errors. What minimizes the square errors here? It's this line. That's what it will find. And actually, I have a computer picture of this as well. So we did this one as well, also in the again, I won't tell you how the secret data is made. Normally I tell you how, but I will tell you how in a minute. So the secret data, I have some recipe, but this is the data, that's the picture, and here is the regressions. Okay, this is like a scatter plot of x1, forget about this. Okay, here it is, y versus x1, here it is, boom. Okay, so you see, positive thing. So this is kind of in disagreement with the intuitive thing that x1 seems to be decreasing y, right? This is telling us that x1 is increasing y, right? If you increase x1, you go up the slope. And it's the same kind of issue as before. It's thinking about multiple linear regressions and which variables are held fixed and which ones are not held fixed. In the question I gave you before, there was an x1 and an x2, and I said, please ignore the x2, and I made a confusing question that way. In this one, I only gave you a y and an x1, and there is no x2, and now I made a confusing question. So what's going on? How do you reconcile your intuitive answer that x1 seems to be decreasing y with this kind of math answer that x1 is increasing y? What's going on? What's the thing? Let me let you chat for a bit. Think about what the hell's going on here. Let me give you a minute, and then we'll all chat together. Okay, time's up. Let's come back together and see if we can clarify the tricky, confusing question. So how do you reconcile the fact that the slope is positive, the beta hat 1 value for y versus x1 is positive, but intuitively it seems like the relationship should be the other way. That increasing x1 seems to be decreasing y. That's what it intuitively seems to be doing. You guys all voted on that on a 16-5 vote, even though the coefficient is positive. How do you balance those two facts? Yeah.
The overall trend is increasing, that's right?
Well, the overall, yeah. So I mean, you could look at this and say the overall trend is is increasing, but like if y is like your grade, do you want to do more x1 or less x1? Like you guys all said we should do less. We want to make our grade bigger, so we do less x1, right? Even though the trend is the other way. So how do you explain that you all voted this way, right? 16 to 5. That's the question. Because this is like real, man. Like if you talk to somebody on the street and you show them this picture, you guys got the right answer. It's not like it's wrong. It's like I think what's going on is there's a mismatch between the intuitive thing and the slope of the coefficient beta hat 1. And it doesn't mean that your intuition is wrong. I think what it means is that interpreting the coefficient is tricky. Okay, that's what it means. But you got to figure out in what way is it tricky. What is the like detail that we're missing here? Yeah.
Our these one estimates has like the other variables baked into it.
That's right. Okay. The other variables. I only gave you x1 and y. What other variables are there? Are there any other variables in this problem? I said there's x1 and y.
Could be that you left another.
I think you all looked at this and your brain immediately saw another variable. So your brain put in another variable just immediately, like within a split second. Your brain looked at this, you're like, yes, there's x1 and y, but there's this other variable, and we're going to think about that one. Yeah.
On the question, the beginning says multiple regression.
It says from the multiple regression notebook. That's the name of this notebook that has this. Yeah. Okay, I guess the way I'm spinning it now is like, I didn't tell you about x2. In the notebook, there is an x2. This is true. There's an x2 in the notebook. I don't want to tell you what I want to look at the picture first. Yeah, this is a good point. What's the variable that your brain added in?
Error.
The error? Well, so the fact that it's not perfect, right? There's errors built in. But when you look at this, you kind of see something. And that something is the reason you saw slopes going down.
Like two populations.
Two populations, right? Your brain looks at this and you're like, aha, there's a secret variable. There's x1, there's y, and then there's, are you in that group or that group? That's the secret variable. Whose group are you in, right? And within each group, x1 is decreasing y, right? This is going down, this is going down. The reason that the slope is positive over here, y equals beta hat x1, we left out the group. No group. Let's say group identity. Group identity is left out. So when someone does a regression, y equals beta hat x1, the math does not know about the group identity, right? You looked at it and you saw there's a group over here and a group over there, and that's how you were thinking. So in your brain, you knew about the group identity. When you do y equals beta hat 1 x1, the rule is anything you leave out varies, right? Right? That's the rule. So beta hat 1 represents everything not in the model changes with x1. So what is the interpretation of this positive slope beta hat 1? When you increase x1, you do two things. You increase the value of x1, but you also change which group you're likely to be in. Okay? So the group identity is left out. In this picture, when you increase x1, it makes it more likely that you're in this group than that group. So what is the value of beta hat 1? Over here, like we said before, this is like the one variable case. And beta hat 1 is equal to, if you did the two variable case, if I included the group identity, let's do that in purple, that would be beta hat 1 with group plus, and then it would be beta hat group times delta group, right? So the thing you're measuring is actually a mixture of two different effects. It's how much x1 affects y and how much x1 affects which group you're in. And that is why this number came out positive. When you increase x1 and allow the group identity to change, it makes it more likely, as you increase x1, you're more likely to be in the large group. And that is why the slope is positive. It's just identifying that as you increase x1, it's more likely that you're in this big group up here and less likely that you're in the small group down there. But within each group, of course, increasing x1 leads to a decreasing y. So that's what's going on here. And in fact, if you run the regression in my little notebook, which I need to change the name of to keep secrets better, in the notebook there is a secret second variable, and the second variable affects the value of y by some constant. If the second variable is bigger than 0.5, then it does one thing, and if it's less than 0.5, it does the other thing. So there is a second variable that is looks like this. Let me see what it's like. Okay. So here is a plot with x2 versus y. x2 is the secret variable that decides which group you're in, and here the fit now is this funny thing. Does anyone know why before the fit was a line, why is the fit like a rectangle now? It's because it's really a plane and we're taking a slice through it. So if you imagine x1, x2, and y going up, we're fitting a line that's like a plane in x1, x2 space, and we're looking at it from the side. When you look at a plane from the side, it's going to look something like this. And indeed, if you know the variables, then you get a better fit, right? So this is one thing to watch out for. This is basically the same exact problem as the first problem in reverse. When I gave you the first problem, there was an x1 and an x2, and I said, please ignore x2. In this one, I only gave you x1 and y, but there is a secret x2 affecting things. And every time you do a linear regression, there are things that are in there that you're including explicitly. There's things that are not there that you're excluding. And there's things like that are there that you've chosen to remove. So you're always choosing which ones to include and exclude, even amongst things that aren't even like mentioned in the data, right? So it's very important to understand this stuff and how they vary. On Wednesday's class, it's going to be all about choosing variables, like which variables you choose and how. That's why this stuff is important. Question here, yeah.
So is it like now more variables we accumulate like to choose to like do this variation by multivariate analysis, then it's good for our...
Yeah, so the problem is sometimes more variables is good and sometimes more variables is bad. And you gotta figure, if it was always one is always better, then it would be easy. You would always do it. And the whole class would just be just do as many variables as you can, or it would be just do as few variables as you can. But the truth is you gotta be careful. You gotta do somewhere in between. Actually, yeah, I think we have time for one more question. Yeah, we have time for one more question. So in this problem, what I'm saying is that you have x1 versus y, and the reason a linear regression with just x1 versus y is bad is because you're ignoring which group you're in. So a better one would be x1 versus y versus which group you're in, and I'll just like add in manually, this is one group, that's one group. I'll just add that in as like a human. Or if you wanted, you could say like x1 versus y, and I'll add a new variable, which is x1 bigger than 5 or not? And those would do better than just x1 versus y. So as a data scientist, you can improve the model by adding the variable. And that variable is which group you're in. And that will have a much lower error. In fact, if you look at, there's some detailed thing, and I'll go through the code at some point too, to show you guys how this code works. If you look at all the output it does, it also tells you the sizes of the error, and you'll see that the error is much better for this, like including this thing. Do I even have this x? Okay, there's some pictures here to kind of make this. But here is the question. This is the actual question I want to ask. New variables. Here's an even better idea. So adding one variable helped, right? x1 and then which group? Why don't we add lots of variables? Here's a new one. Is x1 between 0.1 and 0.2? That's like some new variable. Maybe let's make another variable, which is like, is x1 between 0.2 and 0.3? We can add like 100 variables by just slicing up this picture that we're doing. So whatever picture you get, you can add a lot of new variables. And I just argued that adding a line here and saying this is g1 is x1 bigger than 0.5. This 1, by the way, this is the indicator function. Some people write this as an I. So if x1 is bigger than 0.5, then g1 is yes, like it's 1, and otherwise g1 is no. So g1 tells you which group you're in, approximately. And I just argue that adding in the variable g1 increases the fit. It makes it better. You will understand the model better by doing y equals beta hat 1 x1 plus beta hat g times g. This is a better model. This will get lower error. This is a good model. Better model. Okay. And now the question is, can I just do this again? Like just add a variable for this one, and then a little variable for this group. I'll just add variables all over the place. I'll add hundreds of variables. Okay. What is the issue with this approach? And I believe you have to answer a word. So you have 2 minutes to answer. And I promise you that if you add in a lot of variables, you will actually get a better R² value. I know some people are slaves to the R² god and love to increase their R² value. So if you do this, I promise you will get an R² value that's better. But there is a problem. What is an issue with this approach? Fill in a one-word answer and you have 1 minute. Okay, and this is a great final question. This leads right into what we're doing on Wednesday's class. So we'll do this 1 minute. What is the issue with adding in lots and lots of variables? Okay, and you have to answer within 30 seconds because then the class is over. Okay, time's almost up. The last 5 people, put in your guesses. Let me see what people said. So, oh boy. Okay, so sometimes adding in more variables helps. Why can't you just add more variables forever and ever? The answer is overfitting. Amazing, 11 people got it. It's exactly overfitting. It's the same issue, right? Too few variables would be underfitting. Too many variables would be overfitting. You got to get the right number of variables to get the just right fitting, okay? That's what we're going to do on Wednesday. So, perfect. See you guys on Wednesday.
So we can also say